Okay, so here we go. We're going to talk about food pyramids. This will be on page 7 of your lab notebooks. The top of the page says food pyramids, and we're going to go through this. We're going to give you an idea of what a food pyramid is. And we are going to, sorry, just sit here, all over the place. All right, got to show you, go Bees football. So we're going to talk about food pyramids. We're going to show you an idea of what a food pyramid is and what they help us indicate and go on that. So food pyramids is, and if you'll follow along on page 7, each trophic level is smaller than the one on which it depends, giving a pyramid shape. The base of the pyramid represents the autotrophs or first trophic level. Higher trophic levels are layered on top of one another. So if you look at that pyramid that's right there in your book, you can see that on the bottom of that, we have our autotrophs. So if you remember, again, the autotrophs are self-feeders or plants and algae that can produce their own food. And they're going to use all of the energy that they collect from the sun in order to produce that food. And so they're going to be able to be very efficient. The energy level on which they get from there is 100%. However, as we drop here on the next one, right, and we're going to talk deposit, filter feeders, grazers, right? So the 1,000 units of energy that is shown right here on the first order drops to 100 units of energy for this first level. That's a 10% keep, or we lose 90% of the energy. 90% of the energy from algae, phytoplankton, everything is lost. Most of it is lost as heat or waste, and so we keep only 100 units with those first level. Then we drop to the next unit, these first order carnivores. These fish that eat deposit feeders and grazers and filter feeders, other things, they keep only 10 of the units of energy, so we lose another 90%. We keep 10%. By the time we get up to the second order of carnivores, the fish, the sharks, the things like that, if you look, we only have 1 unit left of the original 1,000 units of energy from those first. And so we're losing 10, or we're keeping 10% and losing 90% on every single level. Now, this next statement says, although you may not see it, it's important to notice that the initial source of energy for an ecological pyramid energy is energy from, I'm checking to see if you remember what that answer is. It's the sun. So remember, all energy on our planet, the energy for me to speak, the energy for me to walk around in Spain, the energy for me to even get to Spain came from the sun. Now the energy for the jet fuel came from the sun many, many years ago. The energy for me to get around right now probably came from that fresh fish that I ate last night that ate the plankton, that converted the energy just very, very, very recently. But all of the energy for you to sit here and enjoy the sweltering heat or act like a fool came from the sun. So all that energy comes from the sun. And I think that's a very important part for us to remember, is that that energy does indeed come from the sun. Now, as we talk about the numbers pyramid, we also see a significant drop in numbers. So if we look at here, the numbers pyramid shows the numbers of organisms at each level. So if you think about this, how many phytoplankton, how many algae do you think there are in the world? And if we look just sheer numbers, the algae outnumber humans individually billions and billions and billions to 1. Okay? What it states is that it represents the fact that there are fewer individuals at each successive feeding level. If there was as many humans on the planet as algae, those algae would never be able to supply enough energy for us because we're so much bigger. So just the sheer numbers alone, right? Think about ants, think about insects, and wonder how many insects are there compared to humans. If we think even in the school, right, where we've got about 12 or 1,300 students, how many different insects are there? And hopefully there's not billions and billions to one on that. But inside the school, because we do a pretty good job of keeping it clean, but planet-wide, there are so many more insects and small, tiny things. Even if you talk, so if we run next door and we ask Mrs. Robinson, how many voles are there out on her ditch bank? And she's told me that as she goes out there and she's swathing or running the tractor, those voles outnumber her hundreds of thousands, maybe even millions to one. So we're so outnumbered on this planet just individually. And there's more insects than there are voles because these voles will eat insects. So that gives you a pretty good idea how many insects are truly on the planet. For grass plant in a given area, there's going to be 2,000 grass plants, just of the plants. Now there's going to be more insects than that. We got voles. We're going to drop down to 25 voles in a given area. So for every 2,000 grass plants, there's going to be 25 voles. There's going to be one barn owl. So just the sheer numbers you can see are dropping significantly. And that's even a little steeper than the 90% decline that we have with just energy. When we get to biomass, what's a biomass? So when you consider biomass, basically what it means is every living thing, so bio means life, so life mass would be weight, so life weight. So we're going to show the mass of organisms at each level. So if we take just a simple beginning one, like the algae, do you suppose that the weight of algae on the planet is greater than the weight of humans on the planet? Just out of practice, turn and tell your lab partner what you think. And hopefully your lab partner, as he or she turned and told you, said that the weight of the algae is so much greater than the weight of humans. Believe it or not, if we're talking just sheer mass, the weight of all the cows on the planet is greater than the weight of humans. And we know that because of our position on the food chain. What we're doing is we're representing the fact that there is less total mass found in each successive level. So those bottom ones, those autotrophs, those producers, things like grass, wheat, corn, alfalfa, all of these in a given area are going to far outweigh any of the other levels. So there's going to be more weight of alfalfa in a field than there's going to be weight of insects in a field. And there's going to be more weight of insects in a field than there's going to be weight of predators of those insects, snakes, mice, whatever it is. And there's going to be more weight of snakes and mice in these predators than there's going to be of predators of them. So hawks, coyotes, things such as that. Each time we're going to drop weight overall. If we look here in the ocean, primary producers are the phytoplankton, these animals that are going to take light and turn it into food. There is 1 million kilograms in a given area of ocean of these producers. Now we're going to drop 90% or keep only 10% of the zooplankton, or these herbivores, these tiny little creatures that are going to eat even smaller creatures. And we're going to lose 90% of the weight of the biomass. Now, when we get to these animals that eat the zooplankton, things like shrimp, we're going to lose another 90%. So there's only 10,000 kilograms of shrimp in a given area of the ocean where there is 1 million pounds of phytoplankton. When we get to the mid-level carnivores, these large fish, the sea bass, things like that, there's going to be only 1,000 kilograms. So 1,000 kilograms in a given area of ocean is going to be, probably, if we consider a kilogram per fish, and even that's a little heavy. Hang on just a second, I'm going to disappear from your screen for a minute. This weight factor here is 1 kilogram. And I'll try and leave this on the desk so you can come and see. But that's 1 kilogram. There's going to be 1,000 of them. So it's still fairly heavy. But when we get to these top level carnivores, we're dealing only with 100 kilograms of weight. sometimes that may not even represent an entire great white shark. So for 1 million pounds of phytoplankton, that area of ocean can't even support one great white shark. Just simply the biomass isn't great enough. We're going to go talk very quickly about the importance of solar energy. Remember, all organisms require energy for metabolism. We went about this what is today? Because I'm recording it on the day we did it. It's Tuesday. Sorry. Wow. Brain fart. But remember, we talked about one of the things that signify life is the ability to burn energy or have metabolism. So the importance of this is that all of this energy that we're using comes from the sun. So when it asks what is the original source of energy in the biosphere, you should all say, whoa, that didn't work right. It's supposed to pop up with the sun underneath. Sorry. And we're bouncing back and forth. Deal with it. So the initial source of all energy is the sun. Okay. The energy pyramid. Now this is again where we show the amount of energy that we have. So it shows the amount of energy stored at each level. General rule of thumb is only 10% of the total energy is passed on to the next trophic level. So if we look at this, okay, energy pyramids, those primary consumers are going to have how much of the energy available from metabolism. And in that blank, you're going to put 100%. When we get to 1C or first level consumers, you can see that we're 10% of the energy. When we get to the 2C or second level, oh, sorry. Go ahead, you guys take a minute and yawn now with me because yawns are contagious. Okay. When we get to that second level consumer, we end up with only 1% of the energy, the original energy from the sun available for us to use. As we lose this 90%, most of it's lost again to heat, energy, and things such as that. When we get to those third level consumers, humans, bears, these top level consumers, we're getting only 0.1% of the original energy of the sun or the original energy that that plant had that we're able to use. Now, how's that going to affect on this next question? Higher level consumers. Let's skip to question number 1 right now, and we'll come back to this real quick. Sorry, just a second here. Actually, let's slow down. We'll talk about the slide. So you're going to get this a little bit twice, and I apologize. I forgot the order that it goes in. So as energy is transferred from one organism to another in a food chain or a web or anything, a large fraction of that original energy is lost. We lose that energy in the form of heat. And you don't have to write this down that I can remember anywhere on here. That's part of the reason I'm trying to follow the lab notebook and make sure. So this part here, hopefully you just took a deep breath and you're like, what? Remember, as you're sitting here in class, you're losing, right? If we were to have a lion break in here and eat you, he's only going to get 10% of your energy. The rest is going to be lost to the heat in the classroom. Each level of the pyramid is smaller, and the space represents the lesser amount of energy available for that. So primary, we've got 100% for metabolism, and this is where you're filling out that space that we just talked about. Okay, we're going to answer these questions in your lab book. You're going to take this time right now, and you're going to answer them with your lab partner. How is the loss of energy going to affect the higher trophic levels? So where you're only getting 10% of the original or of the level below you, and realistic 0.1%, how does that affect you as a higher trophic level? How much more food are you going to have to eat? Why would we be more energy efficient as humans to not eat meat, but to eat lower on the food chain and eat producers? So I'm going to give you just a minute here. You're going to talk about this. As long as it takes Betty to go ahead and load up this next slide you'll have, please be productive and fill that out. And we're going to answer these questions as soon as we get back.